This conference will now be recorded. This conference will now be recorded.
Hello everyone. So last day we have finished diastereomerism, and enantiomerism also we already know. Under optical isomerism we have these two terms, enantiomerism and diastereomerism. Now we have to know another new term which is mesocompounds, and once we have finished mesocompounds, next we'll see one new projection. Just like Newman projection we have seen, Sauer's projection we have seen, one more projection we have to know, which is Fisher projection, and also how to do RS nomenclature in Fisher projection, that we will try to learn. So here we have mesocompounds. What is mesocompound? These compounds, obviously there will be chiral center, but not just chiral center, they will also have a plane of symmetry. So when these two conditions are fulfilled, we can call these molecules as mesocompounds. Now, because of this plane of symmetry, it is ultimately making this molecule achiral. It is true there is chiral center, but because of this plane of symmetry, which is also known as sigma plane, ultimately this molecule will become achiral despite the presence of chiral centers. Here you can see these two pictures. In these two pictures, there is actually no chiral center. It is true that there is plane of symmetry, which is shown with this blue color. So plane of symmetry is present, but you cannot call just any molecule having plane of symmetry, you cannot call meso. The other condition must be fulfilled. There should be chiral center. So that is why, though there is plane of symmetry, but they should not be called as mesocompounds because there is no chiral center. But if you consider the next molecule, here we have chiral center. So these two are basically chiral center, and here we also have plane of symmetry. If you cut this molecule along this blue square, the two half that you will get, they are actually mirror image to each other. So as if the molecule, it's within the molecule there is some mirror. So when you will have this type of plane of symmetry, they will be called mesocompounds. Now we will see example and the relationship of mesocompounds with enantiomer and also diastereomer. So here we have this picture, total 3 pictures you can see here, but try to understand the relationship. If you look at the compound A, we have here 2 chiral center. So these two are chiral center, right? Now in these 2 chiral center, hydrogen is already away from us. We have already known the rules based on which you can decide RS nomenclature. So we'll just use that rules that we have already learned in last class. So hydrogen is 4. Bromine should be having number 1 priority. Now this total group, it will have number 2 priority, and this will be having 3 priority. So 1 to 2 to 3, when you are moving, it is basically anti-clockwise, and that is why it will be S. Now if you see the other chiral center, that will also be S. You can also check it yourself. Now for the next molecule, which is molecule B, here in this case, see the position of H and B are, they are just reversed. And when we know that the two positions are reversed for two groups, now it is no longer S, now it is R. And similarly, this is also R. Here you can see this H and B are, now their positions are as if exchanged. And another way also you can understand A and B, these two are mirror image to each other. If you consider this as the mirror, I am writing here M, you will see these two are mirror image to each other. So another way to understand that these two are enantiomer. But in these two molecules, you will not find any plane of symmetry which can cut the molecule and you can get to similar half both sides. No, you cannot have any sigma plane. But now consider molecule C. In molecule C, if you look at this part, that is the left hand side chiral part, it is just like this, isn't it? So basically this will also be R, because in this left hand side chiral part, as if there is no change. So this is still R. But now if you look at this side, it is as if looks like the right hand side part of A, isn't it? So that is why now it is S. You can also check it yourself. I'm not saying that you have to do it in this way always. So I'm just trying to make you understand that quickly if you want to decide whether it is R or S. So that is why this is a easier way you can do it. So R, it is having some similarity with this part, and S, C, the relative position of H and Br, it is just like the right hand side part of A, so that is what is S. But you can also check it yourself. Here bromine is number 1, hydrogen is number 4, this total group is number 2, and methyl is number 3. So when you are moving 1 to 2 to 3, basically you are moving clockwise, but hydrogen is towards you, so that is why though it is clockwise, but still it will be S, but we have already written here S. Now we know which chiral carbon is S. Okay, let me clear everything and I will write only the R and S. So this is S, S, R and R. Relationship between A and B, these two are enantiomer. Now here it is R, it is S. Now we know if you compare B and C, these two are obviously diastereomer, because we know diastereomer definition, out of many chiral center, at least one chiral center should have opposite stereochemistry. So that is why A is diastereomer to C, B is also diastereomer to C. But A and B are enantiomer. But what is C? C is basically a meso compound, because if you cut the molecule along this plane, suppose I am putting a plane here which is perpendicular to the screen plane of the screen, you will see both sides are actually equal. Both side bromine is away from us, both side hydrogen is towards us, and methyl is on the plane of the screen, right? So that is why this is a meso compound. So though there is chiral center present in this molecule, but because of this internal plane of symmetry, ultimately this molecule will be achiral. So as if within the molecule you are having some mirror image, and that is why this R is now appearing as on the other side. Okay, one more example also we will see. Now it is in Sohars. More examples you will practice. It will basically help you to understand all these different types of terms, because in this chapter it is very versatile, many new things you have to learn. So just practice, especially in stereochemistry you have to practice, and not just looking at the screen or reading any book. You have to practice with pen and paper. Fine. Now the first two molecule, here it is mentioned as enantiomeric pair. Now that you can directly understand if you consider this as mirror. Now you can also decide the RNS. I will just show for one molecule. Now the way that I prefer, and it is also time saving, what you will do, as this lowest priority, it is hydrogen, right? This is hydrogen. This is lowest priority. Chlorine is having number 1 priority. Methyl is having basically number 3 priority. And this total part, that is actually having number 2 priority. Now 1 to 2 to 3, this movement, you have to do it in such a way as if you are looking at the molecule. I am drawing here I. So if you are looking at this molecule from this side, which as if you are looking to the molecule keeping H away from you. If you do so, you will see 1, 2 and 3, this movement as if it will be like this. 3, 1 will be left hand side of yours, 2 will be right hand side of yours. So when you are moving 1 to 2 to 3, basically it is anti, and that is why this will be S. Similarly, if you are looking at the molecule for this another chiral center, if you are looking at the molecule from which side, from other side you have to do it. Okay, so just like that, here hydrogen is here. If you are looking at this molecule from this position, you will easily, you can find the RS nomenclature. I'm not saying this is the only way. You can also convert it to some other that is, you can rotate the molecule or you can convert it to Newman. That is up to you, whichever way you prefer. But this is time saving if you are doing it like this. So this is number 1, this is number 3. You have to look the molecule from this side, and this total group, it is 2. So 1, 2 will be like this. See, chlorine is 1, this total group is 2, and methyl is 3. So as if it is like this, 1, 2 is left of you and 3 is right of you. So 1 to 2 to 3, if you are moving like this, it is and so directly you can get it like this. So here both are ultimately what we are getting, it is S. So S and S, let me clear everything. So both are S. Similarly, if we consider its mirror image, you will see, you can also check it yourself, it will be R and R. So this is SS, this is obviously RR. Now these two are enantiomeric pair. Now come to the next molecule. Here, if you do the similar way, if you follow, if hydrogen is here, so you have to look from this side, and in this another chiral center, hydrogen is here, so you have to look from this side. So if you follow this, you will see this is actually S, this will be R. And though it seems is mirror image, that is I am talking, these two it seems as if mirror image, but really are they two separate molecule or not, that you have to understand. So this is S and R, and this is R and S. You can also check it. I'm just doing it first so that I can move to the next slide. So S, R, and now it's mirror image, obviously RS. But here it is written identical, and it is also written meso. But how it is so? So to understand that how it is so, what we will do, this molecule you can also draw. So I will draw the same molecule in a different way. So what I am doing, I am not changing the carbon which is rear from us, but I am rotating the molecule in such a way so that methyl is now like this. So it is 180-degree rotation. So when you are doing this, you will see methyl will be here, Cl, both the Cl to the same side, hydrogen is also to the same side. Now I'll do also the same thing for the other molecule. I will just rotate it. This back carbon I am not changing anything, so it is still same. But this CH3 now it will be up, and when it is so, H will be somewhere here because it is 180-degree rotation. Cl. Now if you look at this molecule, again it seems as if mirror image, right? But after all, if you cut the molecule along this plane, that is you have to cut it somewhere in this position. This is CC bond, you have to cut in between the CC bond. You will see both sides are actually mirror image to each other, as if this R is mirror image of this S, that is internal plane of symmetry. And that is the reason, though this at a first glance it seems these two are separate, these two are enantiomer to each other, so you may think that these two are having some enantiomer relationship, but that is not true. They are actually identical molecule. And you can also convert this molecule. Suppose I am calling it X and this is Y. X and Y are actually same. How you can do so? You have to simply rotate the molecule. Suppose if this is carbon number 1, this is carbon number 2. If you are rotating the molecule in this direction, now one carbon will be back and two carbon will come here. And these two hydrogens, they will be to the left hand side. So that is why I'm saying now you can understand X and Y both are actually same molecule. So be very careful with meso compounds, because at a first glance they seems as if they are chiral, but you just have to find the plane of symmetry. And if you look at X and Y, basically this is also X, this is also Y. It is true X and Y are same, but I am giving separate names so that because two different pictures are there. So at a first glance it seems X and Y there is no sigma plane, but see, if you rotate this carbon-carbon bond, if you rotate the molecule, then you can easily find the sigma plane. So this sigma plane is through this line. Fine. So this is the way you can decide the whether the compound is meso or not. So these two molecules are enantiomeric pair. Suppose I am numbering it now. It is A, it is B, and just forget about X and Y because they are actually same molecule. So I am numbering it as C. Both are same. This is C, this is also C. Now the relationship. C is identical. Relationship between A and C. This is diastereomer. Relation between B and C. This is also diastereomer. Relationship between A and B. This is actually enantiomer. So now we have seen all the relationship. A with B, A with C, B with C, B with A. Okay. So one more example you will see with the natural compound which is tartaric acid. Here you will be better, you will be able to understand in a better way the enantiomer versus diastereomer versus meso compounds. Here we have taken tartaric acid. Now you can see here how many chiral centers. This is a chiral center. This is also a chiral center. Now I will write the name for this molecule. That is simply nomenclature. Numbering I will start from here 1, 2, 3, and this is 4. So 1, 2, 3, 4. At 2 and 3, these two positions there is hydroxy, and CO2H group has higher priority. So the name will end with oic acid, and hydroxy, these two hydroxy substituents present at 2 position and 3 position. So the name will be 2,3 dihydroxy. It will continue butane, because total, that is longest chain is total 4 carbon, butane dioic acid, because there is 2 CO2H group. And don't forget to give a gap, there will be a gap. So this is the nomenclature, IUPAC nomenclature. 2,3-dihydroxy butane dioic acid. Now as we have 2 chiral center, there are so many possibilities can arise. Suppose the first chiral center it is R, the second one is also R. Another possibility is both S, right? Another possibility is R and S. Another possibility is R, S and R. But ultimately you will see these two will be same. So though at a first glance it seems total 4 possibilities are there, but actually it will be only 3, because ultimately the molecule is symmetrical. Okay, so that is why meso compound will be present also. So this is tartaric acid, and this is a natural compound you can find in grapes, bananas, wine. And remember, the natural form is RR, having RR stereo center. Natural form is only the RR form. So this is the importance of stereochemistry. That is, if you consider some natural compounds in fruits or in anything else, that is, I'm talking about natural compounds, then you will find that when there is chiral center, natural compound having some chiral center, the active compound, that is the natural form, it will always have some fixed stereochemistry. And the if RR is the natural form, SS you can prepare in the laboratory, or the RS form you can prepare in the laboratory. But naturally the compound that you are getting from grapes, bananas and fruits, wine, that will always have RR stereo center. It cannot be any other, because that is the original form. Artificial forms SS, SR, RS we can generate in the laboratory. Now we will see all the possibilities. Tartaric acid. Now this is the natural form, because both the chiral center it is RR. And here you can see this hydrogen is actually above the plane. You can also check it how it is R. Here priority you have to give, that is more priority that will be for OH. So when you are moving from number 1, this will be having number 2 priority, and this total group it will be having 3. So 1 to 2 to 3 it is anti-clockwise, but as hydrogen is towards R, so that is why it ultimately it will be R. And same thing you can also do for the other chiral center. Okay. So in this case we are moving from this to this to this. This is anti, but H is towards us, so this is R. Similarly, now if you consider its mirror image, obviously the RR stereoisomer, that will be now SS, and that has to be okay. So in this way, this now the nomenclature will be different. I have already written the IUPAC nomenclature without considering the RR and SS. 2,3-dihydroxy butane dioic acid. This will be actually a small b. There will be not any gap. So be careful. So 2R, 3R, 2,3-dihydroxy butane dioic acid. So in this nomenclature, we are also including the stereochemistry. Without stereochemistry, it is simply 2,3-dihydroxybutadienic acid. But when you are including it, the natural form is 2R3R, because these two positions are actually 2 carbon and 3 carbon in the longest chain, total 4 carbon. These 2 carbon, 2 and 3. Numbering will be like this: 1, 2, 3, and 4. Now these two are having enantiomer relationship, right? But these two molecule, it can also have diastereomer. Fine. Now you can draw it RS or SR, but ultimately you will see it will have a sigma plane. So don't think this will be having 2. Ultimately this will be only 1. So total 3 isomers possible, stereo isomers possible. So if I am drawing it like this, that is OH, CO2H. Now I will draw this OH like this. Fine. Now hydrogen is here. So what I will do, if you are looking this molecule from this side, suppose as if number 1 carbon is towards you, and I am just converting it to sawhorse. So if it is so, then OH is here, H is here, CO2H is here, and the back carbon, which is number 2, CO2H is in this vertical bond, hydrogen is this side, OH is this side. Now if I am rotating the molecule, suppose the 2 carbon I am just not changing, but I am rotating it in such a way so that CO2H come to the upper position. And when I am doing this, there is no change in the back carbon. See, I have not changed it, but now CO2H is here. And when CO2 is here, H is here, OH is here. Now along this line, if you cut the molecule, both half will be same. So it is having some sigma plane, and because of this, you will see it will be meso compound. And with this meso compound, the relationship of with these two form, obviously the relationship is diastereomer. So again, I am putting here, now suppose it is molecule A, this is B, A is natural form, and if this one is C, the relationship between A and C, diastereomer, and the relationship between C and C and B, that is also diastereomer. Now we will have some physical property which will help you to understand how these their physical property actually varies. So plus tartaric acid and minus tartaric acid. So these two are obviously enantiomer, right? Now for the enantiomer, we know this rotation value, optical rotation value, basically specific rotation, which is you can get in the as a data the chiral compounds. They are, if you check the database, you can find the specific rotation value. So as these two are enantiomeric relationship, if for one form it is plus 13 and 13 degree, other one will be the same numerical value but sign will be reversed. And look at the melting point value. If when you consider enantiomer, their physical properties are same except this rotation direction. But now look at the mesotartaric acid, its melting point. It is completely different, isn't it? And there will be no rotation because ultimately the molecule is not chiral. It is true there is chiral center, but because of this internal plane of symmetry, you can cut the molecule in two similar halves as if some mirror is present internally in the molecule. So that is why we call it internal plane of symmetry. So because of this, ultimately the molecule is not chiral, which is again you can get this evidence. Its rotation is 0 degree. It has to be because it is achiral. How you can get some degree? It has to be 0, and melting point is completely different. So remember, when you are having some enantiomer, physical properties are same, and that is why it is very difficult to separate enantiomer. Suppose you have mixture of A and B, you have to use some special technique, but with simple process you cannot separate A and B from its mixture. But if you have mixture of A and C or B and C, that is mixture of plus tartaric acid with the meso or minus with the meso, then you can separate it easily because their physical properties drastically different. Okay. Now we will compare enantiomer diastereomer. Look at the points one by one. The first point is saying that enantiomer, they will have some non-superimposable mirror image relationship. But for diastereomers, actually there is no mirror image relationship. Whether you and when there is no mirror image relationship, whether it is non-superimposable or that question does not arise. There is no symmetry actually. So no question of mirror image relationship, because there is even if you take mirror image, you will find it is not matching. So look at this molecule. Here it is mentioned that mirror image at this carbon enantiomeric. So this molecule, basically two chiral centers are there, isn't it? Now the first chiral center, that is the upper chiral center, if you focus on this part, you will see, as if I'm just saying, focus on this part of these two pictures, as if there is some mirror and one part is just the mirror image of the other. So mirror image at this carbon is enantiomeric, as if you are considering only this part, they are mirror image to each other. But now consider the other part. Let me use different color. So this other part, if you see, they are having no mirror image. H is away from us, Br is away from us. So there is no mirror image. So not mirror image at this carbon, as if at this part it is diastereomeric. Now consider the overall molecule. These two parts are similar, but that is having mirror image relationship. But overall, when you are considering the molecule, there is no mirror image. So these two are molecules, they are actually diastereomer to each other. You can also put RS nomenclature. It will be clear to you. You will see that out of these two chiral center, one chiral center will be same, other will be different. Now the second point, they rotate the plane polarized light in opposite direction but equal distance. Just consider the previous example, it is plus 13 degree, another one is minus 13 degree. Now in case of diastereomer, they may be optically active, they may not be optically active. When it is not optically active, when it is meso, isn't it? So in some diastereomeric relationship, just take this molecule. When you are considering A and B, these two are enantiomer to each other. There is so second point is plane polarized light. So for A and B, these two are similar. But when it is the meso compound, that is compound C, which is having diastereomer relationship with A, in this case, they will not be optically active. But I'm not saying that diastereomers will never be optically active. It will not be optically active when only when there is some internal plane of symmetry, that is when it is behaving as meso. But they may be they may rotate plane polarized light when they are not meso, right? If optically active, that is the first condition. Suppose they are not meso, in that case they are optically active. Now in that case, they do not necessarily rotate the plane polarized light in opposite direction equal extent. That is not necessary. So just take any two examples. Suppose X and Y, these two are diastereomer to each other, but there is no meso compound. So these two are diastereomer to each other, but none of them are meso compound. Now if X is giving a particular rotation, suppose it is giving plus 30 degree, why not necessarily it has to be minus 30 degree? Because if it is so, then relationship of X and Y, it is no longer D, no longer diastereomer, now it will be enantiomer. So it is not necessary. Number 3 point, similar physical properties, except their behavior towards plane polarized light. So only in plane polarized, the direction is different. Otherwise, if you consider their physical properties, melting point, boiling point, everything is same. But for diastereomers, physical properties are not same. That you have already seen in the previous example, 140 degree melting point for the mesotartaric acid, but for the enantiomer tartaric acid, it is 172. Next point, they have identical chemical properties except towards optically active reagent. When we are having some, suppose we have A and A prime, these two are enantiomer to each other. Now when you are reacting with this molecule, suppose you are treating it with a reagent R. Now R is optically inactive. So in that case, their behavior will be identical. Chemical reaction, whatever product you will get will be identical. But if this reagent R, suppose R is not optically inactive, it is optically active. I am putting a star mark, it means it is optically active. In that case, it is no, that is A and A prime, it will not behave in a similar way. Now they will behave differently. So that is, it is written here, they have identical chemical properties except towards optical active reagents. So for optically inactive reagents, behavior identical. For optically active reagents, behavior is not identical. For diastereomers, they have similar but not identical. Try to understand. Identical means completely same thing will happen, but similar means there will be some similarity. Okay, so some similarity means in the bracket C, usually same chemical reaction. That is, a chemical reaction will be same, but the rate may not be different. So for just take X and Y, these two molecules are diastereomer to each other. When you are treating it with some reagent, optically active or inactive, whatever, reactions will be similar type, but the rate may not be different because they are not having same type of that is stereochemical, the groups positions in of the groups in the chiral center not same, so obviously rate will be different. Next point, their separation is difficult because of similarity in physical and chemical properties. See, when you are trying to separate two molecules, you will obviously use some method, but if and when you are doing some method, you can use a hard reagent or you can use some technique. But if both the molecules are behaving similar way, how you will separate them? Just take melting point. If their melting points are same, how you will do crystallization and you will separate one of them? There must be some difference, right? If their boiling points are same, you cannot use distillation process like this. So there must be some difference in behavior. Otherwise, how you will separate? So that is why their separation is difficult. Only some special techniques are there. Those techniques are not in the syllabus, so we'll not discuss. But there are some separate, there is special techniques. And in those techniques, what we do, we use some optically active compound. Because only with optically active compounds, their chemical properties are not identical. That you have already seen in the fourth point. So that is why to separate them, there is the methods are not very easy to do methods. There are so many steps and you have to do it with some optically active regions. But for diastereomers, it is, they can be easily separated by some physical means because they are boiling point, melting point, there may be density also, all these are different. So fractional, we can do fractional crystallization, distillation, chromatography, etc. If you are, all these terms are new to you, that will also be discussed in this chapter only, because this chapter is some basic principle and techniques. Under techniques, we will have all these terms, you will get clear idea. So diastereomers we can easily separate, but enantiomers we cannot easily separate. We have a question here. So we have to answer which of the following will have mesoisomer also. We'll draw all the molecules one by one. Okay, number one molecule is 2-chlorobutane. So this is butane, and at 2 position we have chloro. So this is the chiral center. You have only one chiral center, that means you can get R or S. But this molecule you will not find, one will be R, another one will be S. But in this molecule there is no sigma plane. That means here mesoisomerism not possible. This is not symmetry. What about second molecule? 2-hydroxypropanoic acid. Propanoic acid is this molecule. Total 3 carbon, prop, ending with oic acid, and the carbon of CO2H group, that is also part of the chain. 2 position is this position. Now this molecule also having just one chiral center. So you can have either R isomer, S isomer, but you cannot find any sigma plane. You cannot cut the molecule in such a way so that you can get two similar half. That is not possible. No sigma. Number 3, 2,3-dichloropentane. Pentane is this 2 position chloro, 3-position clue. This is chiral center. All the 4 groups different. This is also chiral center. But this molecule is not symmetric because see, this side you have only 1 methyl group. This side you have 2 carbon, ethyl group basically. So this is also, you can have basically R configuration here is, you can have R, 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 S, S, R, S, S. So all 4 different stereoisomers possible, but here you cannot have any sigma. So only one option is left, which is 4. So 4 must be correct. Let's draw it. 2,3-dichlorobutane. Now this molecule, you can have some symmetry depending on the relative position of this chlorine and hydrogen. So these two are chiral center, and these two chiral center, just like the previous one, at a first glance it seems you can have all these 4 forms, but actually one form, that is the RS-SR form, ultimately you will see there will be a sigma plane, internal plane of symmetry, and because of that ultimately total 3 stereoisomers possible. But that is not the question. The question is whether it will have mesoisomer or not. So to have mesoisomer, 2 conditions must be fulfilled. There should be some chiral center, and also there should be internal plane of symmetry. Both the conditions are fulfilled for the last molecule. So that is why this will be correct. Here you can see all the possibilities. 1, 2, 3, 4. It is 2,3-dichlorobutane. It is 2 or 3 are formed. That means it is R here. It is also R here. You can also check it yourself. Always, whenever you are seeing any R or S nomenclature mentioned, just check it whether it is right or wrong. Now see, the next one is also R and S, and it will be easier to do because this part as if we have not disturbed. So it is still up, but the other, that is Cl, is now away from us, so it must be S. Now this is S, this is also S. You can also draw the, sorry, yes, you can also draw the, sorry, these two will be enantiomer to each other. That is the first one and the last one. The middle one, you will see there will be a sigma plane. So how to understand that? If you are looking at this molecule from this side, suppose your I position is here, and if I am converting it to, sorry, I will convert it to Sawhorse. Yes. Now H will be here, Cl will be here. This is methyl group, right? Now the back carbon, methyl is here, H is this side, Cl is this side. Let me put number. This is 2, this is 3. You are looking at the molecule from the side of 2. So that is why it will be 2 and it will be 3. Now if I am rotating the molecule, what will happen? So I am not disturbing the rear carbon. Now you can find the sigma plane easily. So at a first glance it seems for this molecule there is no sigma plane, but actually there is sigma plane. So the middle molecule, that will be having some diastereomeric relationship with the first molecule and also with the third molecule. And the last one and the first one, these two will have some enantiomeric relationship. So these 3 are the possibilities for 2,3-dichlorobutane. So this is the correct answer. Last one. Next, we have another question. Given below 2 statements. Statement 1, the compound, you can see the compound, which is compound A. It is saying that it is optically active. Statement 2 is saying, another picture is given. There is difference. At a first glance, it seems difference. At a first glance, it may seem different, but you may also think it is not different. But that you can easily check whether these 2 molecules are same or not. That we can easily check. We will also do so. But it is saying that this one, suppose I am numbering it, I am naming it as B. Though A and B, it may be same. In that case, I cannot say one is A, another one is B, because both are same. But right now we do not know, so suppose this is B. B is the mirror image of the above compound A. So we have to check whether these statements are correct or not. First come to the first molecule. This center is chiral center, isn't it? Why? If you are asking me why, the answer is we have 4 different groups, H, NO2. Now this side we have CC double bond CH3, and you can think this is also CC double bond CH3, then how these two are different? But see, here these two hydrogens are on the same side, but the larger groups, high priority groups, are on the same side. So this is actually Z, isn't it? I'm not saying cis because cis trans and EZ there is some difference. Here we will prefer Z, and the other side these two hydrogens in this CC double bond they are opposite. So this is actually E. Now if it is so, the same molecule I will draw it like this. Suppose this is Z, this side is E, this is NO2, H is here, right? Now similarly I will also do the same thing for B. This is I have done for A, same thing I will also do for B. So this part is as if Z, this part is as if E. Now if it is so, this is NO2, I am not changing the relative position of H and NO2. Now we will try to see the RS nomenclature we will check. H is already away from us. NO2 will having maximum priority because of this atomic number. Now if you are thinking among Z and E, which is to give more priority? Remember Z is always having more priority than E. So 1, this is 2, this is 3. When you are moving from 1 to 2 to 3, this is actually S. What about the next picture? Here this is 1, this is 2, this is 3. You have to do it as if you are away from H. So 1 to 2 to 3, this is also S. So ultimately it seems that both the molecules are actually same molecule because in both cases you are getting S, isn't it? So the first statement that the compound is optically active, this is correct. And second statement that this picture is mirror image of the above compound A. It cannot be mirror image because A and B are not enantiomer to each other. They are actually same. So A is equal to B. So statement 1 will be correct, but 2 is not correct. So option 3 will be the right answer. So just what we have done in this problem, we have simplified the structure like this. We have decided the RS nomenclature, and in this way we have reached the conclusion that they are actually same molecule because in both cases we are getting S. If we are getting S and R, then you can say that this picture is the mirror image of compound, but here actually A and B are not mirror image, they are same molecule. So after finishing meso, next we'll go to Fischer projection. So Fischer projection is another kind of projection. We already have seen Newman, we have seen Sawhorse, but Fischer projection is mainly important in those cases where you have several chiral center, and that is it is very important in carbohydrate where 3 to 4 chiral centers are very common. So in those cases, this type of projection actually helps us to draw the molecule in an easier way. But how to start? In Fischer projection, the 4 bonds that are attached to chiral carbon, it will look like a cross within the carbon atom at the intersection of horizontal vertical. So cross means what? Something like this. So as if this is the carbon which is chiral and it is having 4 different groups. So we will represent the molecule just like a plus sign. And if there is more than one chiral center, we will just extend it like this. Okay, so this is the basis of Fischer projection. Now here you can see we have taken a molecule where there is some chiral center, and with this chiral center 4 different groups A, B, C, D attached. Now if you are looking at this molecule from, just follow this picture, then what will appear? As if C and D is coming to hug you, right? And A and B, they are away from you. So what you will imagine it? as if C and D coming towards you, as if coming towards hug you, and A and B away from you, which is clear from this wedge and dash bond, right? Now we will convert this structure to this simple normal bond, that is a simple straight line like this. But whenever you are drawing this Fisher projection, it actually means this. But we will not use this type of wedge bond or dash bond. We will use simply normal straight line. But the meaning of this is actually this. That means whenever you will have this type of a simple picture, it means actually C and D, which is in the horizontal bond, these two groups in the horizontal bond, actually they are coming towards you. And the two groups or atoms which are in the vertical lines, they are actually away from. You can also have more than one chiral center. So we are just starting with simple case where you have only one chiral center. Okay. So these two horizontal bonds are directed towards you, that is towards the viewer. Now we have another picture. Here we have this molecule where at two position you will have total 4 different groups. So this is bromine, hydrogen. This side we have ethyl group, that is these two together it is ethyl, and this is methyl. This is the ball and stick, that is the same molecule in ball and stick. So black one means it is carbon, the white one is hydrogen, and this red one is bromine. Now if you are looking, just imagine yourself as if you are here, then in your right hand, in your right hand side bromine will be there because you are looking at the molecule, your eye position is here. So just place yourself in that position. Under this condition, H will be left hand side of yours, Br will be right hand side of yours. So now when you will imagine it, it will be something like this. See, in the horizontal bond, H and Br is present, and Br is in the right hand side, H is in the left hand side. And here in the upper position, we have methyl groups. So this is methyl and this is ethyl. Okay. So now you can also see the ball and stick. So here this is the chiral center, and we are representing it. That is, we are converting it to Fisher. So ultimately this wedge bond and dash bond, we will change it to simply straight line, normal. Okay. So same. So in this molecule you just have only one chiral center, but see, you can also have these for more than one chiral center. So here it is mentioned that this picture is equivalent to this, because ultimately these bonds are, all the bonds are wedge. Solid color I am doing. So as if all the Y and X, they are coming towards you, and A and B away from you. Fine. Now this picture, you can also change it to something like this. So here what we are doing, as if if you just shift the molecule, in this case Y is exactly left hand side, X is exactly right hand side, but suppose you have moved it slightly towards this direction, then what will happen, Y will be all the Y groups, they will be away from the screen, that is away from you. All the X, they will be towards you. In this case, all Y, all X towards us. But if you slightly rotate it, it will be like this. And in this case, A and B, their position will change like this. So in this way, from that is the same molecule represented in different way. This is actual Fisher projection. I'm writing here F. F means F for Fisher, where only straight lines will be there, no wedge, no dash. But just to try to understand, if a molecule is given in this way, then you can convert it to this. And better way, if you are still in doubt, suppose a molecule is given in this way and it is mentioned that change it to Fisher, or suppose in 4 options, 4 different Fishers are given and it is asked that which of these Fisher is actually the Fisher projection of this molecule. So this type of question you may get. So in those cases, even if you are confused, the best thing you can do that we'll see next is you can check the RS nomenclature. So for this chiral center, if you check the RS nomenclature, then it will help you to understand whether the 2 molecules are same or not. Because if it is same molecule, all the chiral centers will have same configuration, right? So next we have to learn RS configuration, that is how to do RS nomenclature when a molecule is in Fisher projection. Fine. Now, first thing that we always do for any chiral center, whenever you do RS nomenclature, the first thing that you do, you select the priorities. So for this molecule also, you can ignore this wedge bond. You can simply write it as if the molecule is CHO, because this group is CHO. This side you have chlorine, this is bromine, this is CH2OH. Now, obviously, if we check priority, bromine will be having number 1 priority, chlorine will be having 2 priority. Now, among CHO and CH2OH, CHO is having higher priority. Why? If I am elaborating it, this that is, if it is the chiral center, the next, that is, this chiral center is attached to C, and this C, as if there is a CO double bond, as if this carbon is attached to, how we represent it? We represent it like this: 2 oxygen, 1 H. But for the other group, CH2OH, this carbon that is attached to 2 hydrogen and 1 OH. So that is why it will win over the other. And that is the reason CHO is having number 3 priority and this is having number 4 priority. So now we have already have selected the priorities and you have to trace the path 1 to 2 to 3. So until this point, the rules are actually same. There is nothing new. It is 1 to 2 to 3. This is clockwise and this is R. But why it is there is no difference in rule? The actual reason is we know this vertical bond is actually away from us, and we know when the least priority group is away from us, then simply movement 1 to 2 to 3 clockwise will give you R, and if it is counterclockwise, then it will give you S. But suppose and here the rules are same because the lowest priority group, the least priority group, it is already in the vertical bond. That means it is already away from us. So you don't have to change the rules. But suppose if this lowest priority group, it is not in the vertical bond. Suppose the lowest priority group, it is in horizontal. That means it is towards you. In that case, this CW will change to S and CCW counterclockwise or anti-clockwise, that will change to R. When least priority group, that is group 4, in horizontal bond. Okay. But if it is in vertical bond, you don't have to worry. But what happens in most of the Fisher projections that you will see, most of the time hydrogen is the lowest priority group and that is always present in the horizontal bond. So most of the time this reverse rule you have to apply. If lowest priority group is in the front, that means if it is in the horizontal line, front means it is coming towards you, then reverse the result. With Fisher projections, reverse rule is applied most of the time, because most of the time the lowest priority group that will be in the horizontal bond, and mostly you will see the lowest priority group, mostly that is hydrogen. That is the reason. So in this case, if we take another example, so this example you have only one chiral center, but suppose if I take another example where more than one chiral center is present, then what will happen? How to do the nomenclature in those cases? So here I am drawing a molecule CO2H, 2 horizontal bonds will be there. NH2H, HOH. Okay, so this is a chiral center, this is a chiral center. So in this case, we have to do the RS nomenclature, and remember here we have total 2 chiral center. So first we will focus on the first chiral center. So in this first chiral center, highest priority group you have to decide. The highest priority group will be NH2 because the atom which is directly attached to chiral center, that you have to focus. So that is why NH2 group is number 1. Now after that, CO2H group, that will be 2 and H is obviously 4, and this rest of the part, this is actually number 3. So what we are getting? 1, 2, 4 and 3. So 1 to 2 to 3, the movement is clockwise, but clockwise still it will be S. Why? Because 4 is in the horizontal bond. Now same thing when we will do for the other chiral center. Now which one is highest priority? OH is having highest priority, isn't it? Now after OH, H is always 4. This total group is basically group priority 2. Methyl is basically priority 3 because this carbon is attached to 3 hydrogen, but this carbon is attached to 1N, 1C, 1H. So that is why this whole group is 2. Now what you are getting? 2, 3, 4, 1. So 1 to 2 to 3, it is again, it is now counterclockwise. But though it is counterclockwise, it will be R because 4 is present in the horizontal bond. So we have to reverse the result. Fine. So this molecule, what we are getting, this is S and this is R. So whenever you will have more than, and as per your syllabus, 2 chiral centers are enough. So first focus on one chiral center, then focus on the other chiral center. So we will end the session here. Thank you for listening.